Okay, so I'm starting to record. This is now lecture number 6, I think. 1, 2, 3, yeah, I think this is our end of the 3rd week, and we're a little bit behind, but we're going to start on PowerPoint number 3, which has obviously been there the entire time. Anyone who didn't notice it just must have missed it somehow. I don't know how, because it's so clearly there. But we are going to talk about the rules of counting. Now, I'm sure some of us might be thinking, you know, I might not be good at math, but the one thing that I've always been good at since 3 years old, when my parents said, 1, 2, 3, you're in trouble now, was that I was able to count. Okay, that is not what we mean by counting. Okay, counting, the mathematics of counting is actually a very sophisticated branch of mathematics. Its full name is called Combinatorics. And essentially what it is coming up with formulas and maneuvers and processes for counting things quickly that would normally take lots of time if you did it by just brute force. Okay, so what do I mean by that? If I asked you to count up to 10, then, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, I'm done. That was great. That's not what I mean. I mean something like this. Suppose you take one card from a deck of cards. How many different ways can you take a single card? How many different outcomes are there for a single card?
52.
52, right? Standard deck of cards, there's 52 outcomes, correct? Now, if I said take 2 cards, how many different outcomes are there now? Now, if you can't answer that, that's fine. We'll get into it. But the point is that there's the brute force way, which is ace of hearts, ace of clubs, ace of hearts, ace of diamonds, ace of hearts, ace of this, ace 2, ace 3, I mean, you can list them all and eventually say, oh, it's this many. But that will take you a very long time. Wouldn't it be a lot easier to come up with a formula to do it quickly? That's what we mean by counting. Coming up with formulas to count things faster than just writing them all out and saying, this is how many that we have. Okay, so let's look at the first slide. It says the fundamental principle of counting, which is our very first rule that we're going to use, is based on the concept of multiplication. And when do students learn multiplication? In what, roughly 3rd grade? So the fundamental principle of counting is essentially what is used after 3rd grade. So let's take a look at the next slide and the example that we have here. It says Pat has 4 shirts and 3 pairs of pants. How many different ways can Pat pick a shirt and a pair of pants to wear? Of course, we are not taking into account fashion. So it's not like, well, I would never wear that with that. That's crazy talk. We're not going into that. Okay, just straight up, this person is blind, has no idea about fashion, and just has this many pants and this many shirts. How many different outfits can they wear? Okay, and I'm assuming here that blind people don't know anything about fashion. If they do, my apologies to blind people everywhere. It was just an example. Okay, don't read too much into it. So on this chart, we have 3 pairs of pants. What are the colors of the pants that Pat can wear on this particular day? Blue, black, and white. Right? Those are the 3 pairs of pants that Pat can choose from. And Pat has 4 shirts. And what are the colors of the shirts?
Red, blue, green, and black.
Red, blue, green, and black. So there's 3 pants and 4 shirts. And the question is, how many different outfits can Pat wear? Well, just looking at this chart, it should be relatively apparent that each of those squares represents a different outfit, correct? So for example, the top left square in the chart represents the extremely horrible combination of a red shirt with blue pants, correct? I'm assuming that's horrible because I never see anyone wearing it. So it just seems like it would violate every rule of fashion that exists. If that's not true, my apologies. I don't know anything about fashion. Okay, so based upon the chart, how many different blue jeans? That's a good point. Blue jeans. I didn't think of that. I was kind of thinking of like bright blue, but you're right, right? Blue jeans pretty much goes with everything, right? Like just everything on the planet. So I take back everything I said, except for the fact that I know nothing about fashion. That still holds. Anyway, based upon the chart, how many outfits can Pat wear that day?
With blue jeans?
No. The whole chart, every box represents an outfit. So how many outfits are there?
Oh, 12, yeah.
12, correct?
Uh-huh.
Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which illustrates the fundamental principle of counting, which is if there's 4 ways of doing this and 3 ways of doing this, then there's 4 times 3 or 12 ways of doing them together. Right?
Yes.
Is this also how they count the possibilities for like DNA, not DNA, but it seems like I've seen this in biology, like where they line up like chromosomes or something?
You mean the Punnett squares?
Punnett squares?
Yes, there you go. Thank you.
Uh-oh.
Same thing? Thing.
Maybe. Just because I'm here and you're there, it doesn't mean that I know everything that you don't. I'm teaching you.
Oh,
I don't know anything about biology.
that's it. I'm leaving then.
That's fine. It's okay. I don't want to be here either. So that's totally cool.
Just
Yeah, I know nothing about biology. I have degrees in physics and math, and I take chemistry classes for fun, but biology I can't stand. Pretty much as you hate math, that's how much I hate biology. Okay? So just imagine that hatred, and then you'll understand why I couldn't care less about that.
Oh, we can't be friends.
That's fine. I wasn't planning it anyway. So there's 12 options here, right? 4 times 3, correct? So this illustrates the fundamental principle of counting, which says, I think we can all agree with David about what? If we all left, class will be over. Wow. A mutiny. Crazy talk. Wow. But then I can take a nap. So you know what? Not the worst thing. But anyways, if Pat picks clothes at random, what is the probability that Pat's pants and shirts are the same color? It's a good question, right? Look at the chart. How much?
2 out of 12?
Or 3 out of 12. Wait,
I think it's 2 out of 12.
2 out of 12.
Because it has 1 blue, blue, and then 1 black, black.
Right. And that is the only way. On the count of 3, let's all log on. 1, 2, 3, go. Yeah, I didn't think so. So the answer is out of the 12 possibilities, 2 of them are the same color. So based upon the first chapter probability, all equally likely outcomes, 2 of them give us what we want. So the answer is 2 out of 12. Let's look at the next slide. It says, let's look at this in a different way. We love math here. Oh, what a lie, but so sweet. Okay, so use this tree diagram to count the number of outfits. Okay, so tree diagrams are a very important tool, not just here, but also in more advanced situations. And they are used when you have different events that occur one after the other. In this particular situation, he is, or she, Pat, is first picking a shirt and then picking a pair of pants. So if you look at the first decision, which is the shirt, we have 4 options: red, blue, green, and black, correct? That's based upon the previous slide. Once that decision has been made for which shirt you're wearing, there are then 3 options for which pair of pants. And those 3 options occur for each one of those first options, which is why along each of the 4 branches in the first step, you have 3 branches emanating to the second step. Blue, black, white for red, blue, black, white for blue, blue, black, white for green, and finally blue, black, white for black. Does that make sense? So the tree diagram just gives us a visual aid for the same situation of how many different outfits can this person wear. You multiply 4 times 3 and you get 12. Does that make sense so far? If we look at the next slide, it says the Honda Civic LX comes in 2 interior colors and 8 exterior colors. So construct an area model to illustrate the number of different combinations. The area model is that first chart that we had where the squares all have areas. How many rows and how many columns are we going to have in our area model?
2 and 8.
2 and 8. Or 8 and 2. Doesn't really make a difference. It depends. I mean, here, obviously, the space is wider than it is taller. So I would have the 8 go sideways and the 2 go up and down. Right? And those 8s are given there. The colors are kind of hard. I mean, as far as I can see, like half of them are the same. I see red, blue, black, white, and then 2 browns and 2 grays. I don't know. I don't know. I'm not good at color. Maybe I'm colorblind. But there's like 4 different colors. What would those colors be? How would you describe the top left color?
Dark silver.
Dark
Gray.
Dark silver gray. But if you do gray, isn't the bottom right also gray?
Dark gray.
Yeah, so you can use
Slate.
whatever. Slate. Damn. Slate. Ah, that's what I'm talking
Slate.
about. Awesome. Slate. Wow. I never in a million years would have come up with that one. Let's see, my old car was taupe. That's right. I had a Jeep years ago. It was taupe. Right? Not dope, although also dope, but it was taupe. That was the color. Anyways, so we have the area model. And then if you want to do a tree diagram, what are the 2 different types of tree diagrams that you can do?
One starting with interior,
Exterior and
and starting with exterior.
Beautiful. You can either, now which of them is which of them do you think is a smarter way to do it? Less
The
work.
one with the least amount interior because it has only two colors.
So would you do interior first or exterior first?
Start with exterior.
Exterior.
Good. Exterior first, so the 8s, you only got to do 1 time, and then a bunch of 2s. As opposed to the 2 1 time, well, it's only 2 8s. Actually, it's probably the same amount of work. I don't know. It makes a difference. That's the point I'm trying to make. You do whatever one you like, whatever one is the least amount of work. So in this case, Ashley, I'd probably do I'd probably do the 8 too. So any questions so far on area diagrams and tree diagrams to illustrate the fundamental principle of counting? So far easier than the previous chapter, I hope. It was very abstract. This one is counting. What? I don't know how to count.
Professor,
Yes.
with this, we can actually see that it comes out to be 16 different. Okay.
You should.
All right. That's what I wanted to verify.
Yeah. Okay. So look at the next slide, number 5. Here we're now summarizing the rule. It says that there's A ways to do one thing and B ways to do a second. Then there are A times B ways to do both of them. And if there's C ways to do a third, then A times B times C ways to do all 3, and so on. So if you're picking a shirt, pants, hat, shoes, which car you're going to drive today, because we all own the Lexus and the BMW and the Lamborghini, you got to pick which car you're going to drive. And, it can go on and on. Do I want to go morning, afternoon, or do I want to go in the evening? Do I want to take this street or that street? You can do so many options. You can have a chain of as many as you want. And the first principle, the fundamental principle of counting says You just go in order. This number of ways times this number of ways and this number of ways and so on. So it says use the fundamental principle of counting to count the number of ways a sequence of 5 flips can turn out. In this case, I assume when they say flips, they mean the flip of a coin. So we're flipping a coin 5 times in succession. First flip, how many outcomes? 2.
2.
Second flip, how many outcomes?
2.
2. Third flip, how many outcomes?
Let me guess. 2.
Good guess. Fourth flip, how many outcomes? 2. Fifth flip, how many outcomes? 2. So what does the fundamental principle of counting say is the number of ways that these 5 flips can turn out? Multiply across. 2 times 2 times 2 times 2 times 2. What do we get? What does that mean?
Like 10?
10. Not 2 times 5.
Sorry, hold on. My brain just like.
I understand. I see that a lot. So, how many?
64 times 5. I'm not that quick.
Neither am I. So, what do we get?
I'll tell you.
How much?
320.
320. What?
I don't know.
Neither do I. How many ways?
Okay, so we flipped it 5 times.
Yes.
Each time we get 2 results, right? Two possible results.
Right.
2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 36? No, 2?
We do 2 to the
32.
power of 5.
32.
Oh, okay.
So, what was that question?
We do 2 to the power of 5.
2 to the power of 5. Right? 2 times 2 times 2 times 2 times 2 ends up being 2 to the power of 5. 2, 4, 8, 16, 32. So there's 32 possible outcomes, all of which, by the way, are equally likely.
Okay, I have a question. How
Yes.
would we know that we have to do 2 to the power of 5 and not multiply 2 times 8 like the other chart?
Because the 2 times 8 was 2 things. One had 2 options. One had 8 options.
Yes.
Here we have 5 things, each of which has 2 options. You multiply the number of options. 2 options times 2 options times 2 options times 2 options times 2 options.
Okay, I get it.
Right?
Yeah.
Now, what is 2 times 2 times 2 times 2 times 2? It's the same thing as 2 to the 5. Right? That's what it's equal to. But
32.
32. So what is the probability of getting all heads in 5 flips?
5 out of 5? No, 5 out of 32.
So there's 5 ways of getting all heads in 5 flips.
1 out of 32.
1 out of 32. There's only one way to get 5 heads in 5 flips. Correct? Miriam?
Yes, yes,
Only one way to get 5 heads, right?
yes.
There's 32 outcomes, all of which
Oh,
are equally
yeah.
likely. Only
Good
one of them
call.
is all 5 heads. That's just
Okay.
head, right?
Sorry. I was
forgive you.
thinking of
Okay.
something else. It's a coin, so it's one side. Yes.
I understand. Now, could an area diagram have been useful here?
Yeah. Wait,
Really?
no.
It'd be
How?
too big, right? Huh?
Now, the issue is not really how big it is. I mean, it could take, it could take the entire wall in front of you if you want. I don't care. But can you do an area diagram for a situation where there's 5 successive flips?
No, so you have to use a chart like the previous.
Yeah, you have to use a tree. Because remember, first option, second option, where's the third option going to go? You've already taken up the whole page, both dimensions. You want to go into the third dimension? Sure. How about the fourth option? Where are you going to go now? We don't live in a 5-dimensional space. It doesn't make any sense. Area diagrams only work for 2 occurrences. First, whatever you do first, whatever you do second, or vice versa, that's it. Once you go past 2, you can only do it with a tree diagram. Now, this tree diagram would be very annoying. Right? What would it look like? So let's start right here. Can you all see this?
Yes.
Okay. First flip. What are the outcomes?
Heads or tails?
Heads or tails? If I get a head on the first flip, what are the possible outcomes for the second flip?
Heads or tails?
If I had gotten the tails on the first flip,
Heads or tails?
if I got heads and then heads, what's the possibilities for the third one?
Heads or tails?
Same thing.
How about if I got heads and tails?
Same.
Heads, tails.
Now, for heads, 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 it would be heads or tails, heads or tails, heads or tails. You can see that the further you go here, the tree just gets larger and larger and larger, right? In theory, you can do it, but it's really annoying. Which is why we'd love to instead have just basic math. 2 times 2 times 2 times 2 times 2, 32, done, without having to write it out, correct? Okay. So let's look now at slide number 6. New concept. The fundamental principle of counting is now over. Are there any questions on the fundamental principle of counting?
So is this how you figured out when we were doing the probability flips? You were like, oh, you're going to have 16 total. This is how you figured it out.
Exactly.
Yeah. Oh, okay.
I see that, huh? Exactly. So, okay, permutations. A permutation is more complicated, excuse me, than the fundamental principle of counting. Okay, you don't get any easier than the fundamental principle of counting. So everything other than that is going to be harder by very definition. And permutations are the first more sophisticated situation. So let's look at the example that we have here. Have you ever seen this type of toy, this child's toy? Okay, I have one myself. I like to play around with it every now and again. So this toy for children has 6 rings of different colors and different widths that stack on a post. And the purpose of the toy is to have the children stack them from widest to smallest, correct? That's the basic idea. How many different ways? So let's say all the 6 are off the post. So we have the post sitting there and we have the 6 rings that are just hanging around. How many different ways could the child select the first ring to fit on the post?
6.
6. Right? Any one of the 6 rings, correct? Only one of them is correct. And what I mean by correct is the design of the toy. But any of the 6 could fit on the post, correct? Okay. Now, once you've chosen that first ring and it's on the post, the next question is, how many different options are there for the second ring?
5.
5. The first one is no longer an option for the second ring. It's already on the post. First one's gone, right? You used it. It's there. Now there's 5 sitting around. I can do any one of those 5 can go on top of it, right? Now, once those 2 are there, how many options are there for the next one?
4.
4. And once those 3 are there, how many for the next one?
3,
And then the next one?
2,
And then the next one?
1.
So, by the principle of counting, how many different end configurations could there possibly be?
You add all of them
Oh, you
together.
add all of them.
Where does adding come into play? Fundamental principle of counting. You have successive occurrences, one after the other. What's the rule? What do we do? What do we do?
Multiply.
We multiply. We multiply.
You multiply all the numbers?
Well, that's the rule, right? If you have a sequence of occurrences, all of which have a certain number of options, you multiply all those numbers till the end. So what do you get?
720.
720.
720. So there's 720 different ways that the 6 colors could end up. It says, what rule did you use to compute this?
Permutation?
No.
No.
Yeah, you didn't
The
use that rule.
fundamental
The
principle.
fundamental
of
principle of counting. That's what you used. Right? You multiply them all together. Now, the largest ring is supposed to be put on first. The second largest ring is supposed to go next, and so on. Now, suppose the kid's an idiot and put him on at random. Okay, what is the probability that the rings will magically be in the correct order?
1 out of 720.
1 out of 720. 720 equally likely outcomes, and only one of them is correct, right? So if this kid magically got the right one, I'd have to say the kid probably wasn't as dumb as I thought, and the kid really knew what he was doing or she was doing, because the 1 out of 720 is a very small chance of getting it magically. So small that if it happened, I would say, yeah, you know what, this probably didn't occur. Does that make sense?
Yes.
Okay. Now, let's take a step back for a second. How many ways are there to put on just the first 2 rings?
30.
30. Excellent. Because remember, the first
What'd you
ring is...
get then?
Well, you think about it. If you're only looking at the first 2 rings, how many options for the first one?
6.
How many options for the second one?
5.
6 times
Oh,
5,
and
30.
multiply those. Okay.
That's the fundamental principle of counting, isn't it? You
That's what
multiply.
we were talking about.
That's crazy. Now, how many ways are there to put on just the first 3?
120.
20.
120, right? Again, the fundamental principle of counting, correct?
Yes.
So let's now define exactly what we mean by a permutation. Okay? The first thing we're going to do is we're going to define a mathematical operation. It looks like an exclamation point. Okay? Anyone know what the exclamation point symbol, the word we use for it in math is? Anyone ever seen that before? It's called factorial. F-A-C-T-O-R-I-A-L. Oh, no, I saw that. Yeah, right. Come on. Sure you did. Oh, yeah, that's what I meant. Yeah, right.
No. I remembered it. It's like one of those, like when someone says it, you remember it kind of thing.
Yeah, same.
Like your birthday. I got it. Okay, I'm with it. Okay, so factorial. So n factorial literally means n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times all the way down to 1. So if I wanted, let's write out a few of them here. One factorial means multiply every number starting with 1 all the way down to 1. Well, since you're starting with 1, then all you get is just the number 1 because you're already there. 2 factorial, starting with 2, multiply down to 1. So 2 times 1, what do you get?
2.
2. 3 factorial means multiply every number from 3 down to 1. What do you get?
3.
No, 3 down to 1
6.
multiplies 6.
6.
4 factorial,
24.
24. 5 factorial,
120.
120.
Sorry, can you just write that out just for the sake of like getting the pattern here? So
Sure.
1 I understand is 1. 2 I understand is 2. And then oh, I see. Okay. 3 times 2 times 1.
So the next one would be times
720.
6 factorial 720.
And so on. And since you're all going to be teachers, hopefully, and you're going to want to impress your students with your mathematical acumen and knowledge, I'll even give you this one, which isn't in the book. 0 factorial is also 1. Not because it follows the same pattern. You can't go 0 down to 1. You're already past 1. It just makes no sense. It's just a fact that 0 factorial is equal to 1. So if your students ever say, hey, what's 0 factorial? You can say, oh, that's equal to 1. And they're like, what? Why? And you're like, well, I had this amazing professor in college who told me this, and he didn't explain why, that bastard, and now I don't know, and it keeps me up at night, and it'll keep you up at night too, so suffer like I do. Something like that. You know, I mean, you could use your own words, but that's the basic gist of how you want to explain it to your students. So 0 factorial is 1. So anyways, let's read this box. It says, there are n factorial, which is n minus 1, n minus 2, all the way down to 1, ways to line up n objects. 6 for the first, 5 for the second, 4 for the third, 3 for the next, second, 2, 1, 6 times, down to 1, right? That's what we did for the toy, correct? So that's the number of ways you can line up that many objects. But suppose you didn't want to line up that many objects. Suppose you wanted to line up less than that many objects. Suppose you have 6 objects in front of you, but you only want to line up 3 of them. So if you only want to line up only R of the n objects, then you would only do the first R factors. Now, this is a little more complicated. So let me try to write this out so you can see it. Where did my marker go? Where did my marker go? Oh, here's okay.
Is it in your pocket? I thought you had it.
Not in my pocket. But I have a whole drawer full of them, so I'm good. Okay, so suppose you have 6 objects and you want to use 3 of them. So, first slot, second slot, third slot. How many of those 6 objects can go here in the first slot?
Six of them? You can choose.
Any one of those 6 can go in the first slot, right? You have 6 options. I mean, obviously only one of them ends up there, but you have 6 options. Once that one has been fixed and chosen, how many do you have for the next slot?
5.
5. And once those 2 have been fixed and chosen, how many do you have for the next slot?
4.
4. So by the fundamental principle of counting, this becomes 6 times 5 times 4. Correct? Now you'll notice that if I use 6 times 5 times 4, I can't use this factorial thing because I don't go down to 1. And the factorial always goes down to 1. Correct? So I'm going to do a little trick here. I'm going to throw in times 3 times 2 times 1. The problem is that that's, of course, not the right answer. Right? I just threw in some extra numbers. Of course, the answer is going to change. But what if I also divide by the same thing? What happens to these numbers if I do this on top and on bottom?
It can't.
They cancel out.
So mathematically, it's correct, right? Right? From a mathematical standpoint, it should give me the right answer, right?
Yeah.
The question is, why would I want to complicate things? And the answer is, well, you're not complicating things. Because now look at the top. The top is now 6 down to 1. I can just write it as 6 factorial. And the bottom is 3 down to 1. I can write that as 3 factorial. So if I want to use 6 objects, and I only want 3 of them, so this wasn't the greatest example. Unfortunately, in hindsight, I see that now. because this 3, you might think it's the same thing as this 3. So I want to change the problem a little bit. I'm only going to use 2 of them. Okay, so I'm only going to use 2 of them. So let's go through this and fix it. I apologize. So again, 6 objects, but I only want to use 2 of them. How many options for the first one?
6,
How many for the second one?
5.
So it should be 6 times 5, correct? That should be my answer. What I'm going to do is I'm going to throw in on top 4, 3, 2, 1, and on bottom 4, 3, 2, 1. Do you agree mathematically these are the same? Why did I do that? Because the top, I can now write simply as 6 factorial. And the bottom, I can write simply as 4 factorial.
Oh, got
Okay?
it.
So when you have n equals 6 objects, when you want to use r equals 2 of them, and this is the number of ways that you can do it. You take n factorial, you do n minus r factorial, and then you divide. And when you do that, that will give you the number of ways that you can pick r objects out of 6.
So that's our formula.
That's your formula.
Okay.
That's the formula in the box. And what we're going to do now is a few examples. And these examples are going to illustrate the formula in the box. Okay, we're going to do some examples to illustrate the formula in the box. So, question number 1. How many ways can 5 teachers be assigned to 5 classrooms? How many ways can 5 teachers be assigned to 5 classrooms? So let's think about it. What is n here?
5.
5. And what is r here? How many of those 5 are we using?
5.
All 5. So n and r are both 5. Okay? So if n and r are both 5, what does the top become?
5.
5 times 5 factorial.
5 factorial. And if n and r are both 5, what does the bottom become?
5 minus 5 times factorial. I guess
So
you
5
can.
minus 5 is how much?
1 factorial?
One,
Not
no,
1.
0.
5 minus 5 is how much?
0.
0,
0 factorial,
which is
Oh,
Got the
the
plus
1.
1.
which is 1. 0 factorial is just 1. I told you that, right?
Yeah.
That's just 1. And what's 5 factorial?
5.
No, 5 factorial.
-5.
No, we don't get a negative number.
120.
120.
Oh, because you did the 5 times 4 times.
5 times 4 times 3 times 2 times 1. We did it a few minutes ago.
120 over 1.
So it's
Hold
really
on.
over 120.
I have a question.
Yes.
How did you get, okay, over here with the n minus n factorial.
N minus r. N minus r factorial.
N minus, okay, I see what you use. So it's n factorial divided by n minus r.
Factorial.
Factorial, okay.
Correct.
And then in the box in our slide where it says combinations, right next.
Wait. We're not ready for combinations yet.
Oh,
We'll get to combinations later. We're still working on permutations. We're on slide 7 right now.
oh, sorry, my bad. I went ahead.
No problem. No problem. So how many ways can 5 teachers be assigned to 5 classrooms? The answer is 520. So now it says 5. Question, David?
I thought it was 120.
Yeah, 120.
Oh, you said 7.
You said, I thought you said
Oh,
520.
520.
My apologies. 120. That's what I meant.
120.
120. Okay. So now, 5 teachers are to be assigned to 2 classrooms. Sorry, I'll try that again. 5 teachers are to be assigned to classrooms, but only 3 classrooms are available, so 2 teachers will have to wait. How many ways can the assignment to available classrooms be done? So we don't need to do math here. We can always, for small cases like this, we can always just write it out. Right? You have, how many teachers do we have?
5.
5 teachers, right? There's 5 teachers. And how many classrooms are there?
3.
3. Classroom 1, classroom 2, classroom 3. How many options do we have for the teacher that's going to be assigned to this classroom? 5, right? Any one of the 5 can be in this classroom, correct?
Yes.
Once this teacher has been assigned this classroom, how many do we have for this classroom?
4.
4.
And once those 2 have been assigned, how many do we have for the third classroom?
3.
3. So how many different ways in total can we assign these 5 teachers to these 3 classrooms?
60.
So it's 5 times 4 times 3, which is 60, correct?
Yes.
Which is also 5 factorial over 2 factorial. Because n is 5 and r is equal to 3. We're only taking 3 of those 5. Right? We're picking 3 of those 5 objects. So 5 factorial over 2 factorial gives you 60. So you can do it by a picture and writing it out, or you can do it by the formula. Which is better? Well, the formula is better because you can't always do it by a picture. If I said we have 70 people and we have 42 classrooms, you're not going to want to do it by a picture. Right? The formula is a lot faster once you understand the formula. Let's do the last one.
Can I ask a question?
Yeah.
Just like in reading, like word problems or whatever, just
Yeah.
real quick. So you just, for the n, you just look at, is there like a rule of thumb for what the n is?
Well, the n is the number of objects that you're picking from.
Oh,
And,
you said that.
and R is how many of those objects we're picking.
Okay.
So in this example, we're going to pick 3 teachers out of those 5. And those 3 teachers are going to get classrooms. Correct?
Yeah.
So there's
Okay.
5 objects, and we have 3 teachers, so n is 5, R is 3. And n always, R can't be bigger than n. You can't pick more teachers than there are available.
Yeah.
So if you have 2 numbers, n's always the bigger one.
Okay.
Professor,
Yeah.
for the bottom part of the 2 factorial,
Yeah.
do we have to write that out afterwards?
No. I mean, 2 factorial is just 2. 2 times 1, right?
Right.
So just write it as 2.
Okay. Thank you.
So
Yeah.
for the last one, we would do 5 factorial over 7.
Why 7? Where do you get 7 from?
It says 7 classrooms.
Oh, I haven't looked at the last question yet.
Oh, okay.
I haven't looked at it yet. But even before I look, you said nothing about factorials in your answer just now. So I
said
can tell you
5
right now it's wrong, right?
I said
There's
5 factorial.
over 7.
Yes.
7 what? 7 factorial?
Yeah.
Well, you didn't say that though,
Oh, okay.
right? But even that is wrong. I know that for a fact because the bottom can't be bigger than the top. So let's go into it and see what's happening here.
Professor, real quick question. Does the factorial continue on into the 10 factorial, 12 factorial, 15 factorial? It just goes on forever, correct?
Forever.
Okay.
There's even
If you say infinite.
factorials for fractions.
Yeah.
And for negative numbers that are way more complicated than we need for this class.
Okay.
Okay, and way more complicated than you're going to need to teach, elementary, middle school. Okay, but I'm a big believer in the teacher should not just know enough to teach this material, but should have a deeper understanding of it. Unfortunately, in this case, that deeper understanding is really deeper understanding, and you don't have to worry about that. But if they ever ask, you should know enough to say, yes, you can do that, but we're not going to.
Understood.
Okay, which is perfectly valid answer. Is just, it exists, and hopefully one day you'll get to it. Okay, next question. It says 5 teachers are to be assigned to 7 classrooms. So 2 classrooms will be left over. And the question is, how many ways can this be done? I'm not going to say the answer. I want you to think about the answer. But just remember that whatever you come up with, it has to make sense. Which means your final answer cannot be a fraction, can't be a negative, right? It's got to be like, 17, 26, 82, 117. Whatever the answer is, it's got to be a number of ways. A number of ways has to be a whole number. So if you come up with what you believe to be the correct answer and you put in your calculator and you get 0.6, for example, that obviously cannot be true. So try to come up with and you can use pictures or use a formula, I don't care which way, but try to come up with a reasonable answer to this question for how many ways 5 teachers could be assigned to 7 classrooms so that 2 classrooms are left over.
So then are the teachers still our n factorial?
I'm not telling you. I want you to think about this. This is a new problem. No, but here's the whole point. The whole point is this, is that don't always assume every question is a repeat of the one that came before.
Okay.
Every question that you come across, you should say to yourself, how do I answer this question? Not how is this like the previous one, but how do I answer this one?
Okay.
And that's the approach you should always be taking. Otherwise, you're just memorizing.
Okay.
And memorizing, you forget, and then you're over. But if you understand, then you can always recreate whenever you need to.
All right. Thanks.
No problem. It is gross. 20 ways, huh? Okay, well, at least it's a whole number. I like my hamburger yesterday. That was good. It is disgusting. Pears? Why does anyone eat this crap?
Is it 60?
I don't know. I haven't done it yet.
Oh, okay. Well,
But the fact that you got a whole number is a great sign. Doesn't mean you're right, but getting a whole number is wonderful. But I don't think it's 60, but I haven't done it yet.
I have one question regarding the one with the 5 teachers are to be assigned to classrooms, the one
Yeah.
before this.
Yeah.
So it says 60, right? That's the answer?
Yeah.
Okay, perfect. That's all.
60, right? Okay.
I don't understand why the 2 classrooms are going to be left over. Is that because there was
Well,
enough
There's 5 teachers, so there's 7
5
classrooms.
teachers?
I mean,
It
what you
seems redundant to say that there's going to be 2 classrooms left over.
Well, it is redundant because had they not said it, you would have known that there was 2 classrooms left over.
I
Correct?
don't understand why it's in there.
I will bring it up with the math textbook committee, and we will I will give a flaming report based upon your observations.
Okay, great.
I love your sarcasm.
Huh?
I love your sarcasm.
Oh, thanks. I kind of like it too. Except when people get upset and they complain about me, then it's not good. Which happens more than you realize. But I'm still here after 20 years, so they ain't firing me yet. Mm. 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 Okay. All right, so we have 20 of the possibility. If you have another answer, put it in the chat. Someone said 60. Write that to Miriam. I think that was you, right? You said 60? Right there. 26, 20, 60. Okay, what else we got? 120. I want to hear all the possibilities. Don't just randomly say like, oh, 17, pi. I mean, make sure there are things that you came up. Oh, 26, 20 twice? Oh, no, 25, 20 3 times, 4 times. It's scrolling too fast. I can't even count how many times. 1, 2, 3, 4, 5 times. 42, if we use 7 factorial. Maybe we do. I don't know. I see a lot of 25 20s, though. Some 60s, some 42s. That's the answer to life, the universe, and everything. Hopefully you guys all know that. If you don't, you're too young. David, you should know it, right? You know it, right? Okay. Me and you, we're the old people in the class. I mean, I'm better looking, but, we're both old. So.
I'm oldest.
Lori, what are you talking about? I don't believe it.
Yeah, believe it.
You are definitely not older than David.
Pretty sure.
No, I don't believe it. I don't believe it. But you know what? It's not the age, it's the mileage.
It's all relative, exactly.
It's all relative. All right, so let's do this problem, right? So let's see what we get. Let me see the question again. The question was, 5 teachers are assigned to 7 classrooms. Now, the first teacher gets the pick of the litter. How many different options could the first teacher go to?
7.
Any one of the 7 classrooms, correct? So the first one can go to any one of the 7. So there's 7 options for the first teacher. How many options are there for the second teacher?
6.
6.
How many for the third teacher?
5.
5,
How many for the fourth?
4.
4,
For the fifth?
3.
3,
So 7 times 6 times 5 times 4 times 3. 7 times 6, that's 42. 5 times 4, that's 20. 42 times 20, that's 840. And 840 times 3 is 2420, 520. And there were a few people who said 2520. A few people got that right. Oh, I see someone's really happy. Raise the roof. Yeah, they're talking about. So our Pine's really excited right now. Oh, Angela, you go, girl. That's what I'm talking about. So I have 1, 2, 3, 4 people who wrote 2520. Does that make sense how I did it, how they did it?
I did it a different way, but I got that same answer.
Well, the easiest way, I think, would be to recognize that in this problem, the people in the classrooms are flipped. We're picking, unlike before, where the teachers were assigned where the classrooms were assigned to the teacher, here it's more the teachers are assigned to the classroom. So we're taking n is equal to 7. There's 7 classrooms. And R is equal to 5. There's 5 teachers. So we're picking 5 of the 7 classrooms. So it should be 7 factorial over 2 factorial. Right? We're picking 7. We're picking 5 out of 7. 5 out of those 7 classes are going to be picked. So the math says 7 factorial over 2 factorial. What is 7 factorial? 7 times 6 times 5 times 4 times 3 times 2.
5040.
5040 divided by 2 factorial is 2520. One way is the brute force way, and the other way is the formula way. And both of them are important and have their uses, and ideally, you should recognize how to use both. In this case, there's really only 2 numbers present, 7 and 5. The bigger one is always going to be the n. So 7 factorial over 7 minus 5 or 2 factorial, do the math and you have your answer. Hopefully that makes sense. You'll have some homework on it, of course. So now let's move on. Unless there's a question. Is there a shortcut for factorials in the calculator? Yes, there is. Depends on which calculator you have. What calculator do you have?
Your
The TI-84. Wonderful. Here's what I want you to do. Ready?
Wait a minute.
We're going to do 7 factorial very quickly. So hit the number 7. So on your screen should be the number 7 because we're going to calculate 7 factorial. You with me?
I can't get the cover.
Oh, well, I guess you're not with me then. Okay, so now hit math. Hit the math button. Math button's on the left side of the calculator, a little above the middle. You guys see the math button?
Can't
Hit
find the
math.
factorial.
Well, no, just the math button.
Oh, 7 math.
Yes, 7 math.
Okay.
Now, you should see a screen that looks like this.
Yeah.
Okay, I want you to scroll to the right. Not there, but there.
I saw it. Okay.
Okay, so go to prob. And what do you see?
Number 4 is the
So go down to number 4 and hit enter.
enter. Oh, cool.
And then hit enter again.
So fancy.
Yeah. Yeah, those
are you
calculators
supposed
from
to-
50 years ago are really amazing, huh?
Are we supposed to press on back?
On what?
FRAC?
Well, no, math, you got to go to the right.
Okay, math.
Then you go to the right. You got to hit the right button, this thing here.
Okay, it says PRB.
to PROB, yeah.
Yeah.
And number 4 should be an exclamation point.
Okay.
So you go down, scroll down to 4, hit enter,
Okay.
hit enter again,
Oh,
and
nice.
that's your answer.
I learned
you get-
something new today.
You know what? A day without learning something new is still a day. Okay, so let's go let's go down to the next slide, which is combinations. Okay, combinations. Okay, so what's the difference between a combination and a permutation? They are very different, but they're very similar. So they're very different and very similar at the same time. What do I mean by that? There is one difference between combinations and permutations. For permutations, the order matters. For combinations, the order does not matter. Write that down. That's pretty much it.
Can you please repeat that?
Can you repeat that, please?
For permutations, the order matters. And for combinations, the order does not matter.
Thank you.
Okay. So write that down. Of course, the formula is going to be different too because of that. So the formulas are similar, but at the same time, the formulas are different. So let's look on the slide on page, on the next slide 8. Okay, the box, combinations. If you don't care in what order they are selected, then there are n factorial over n minus r factorial. That's the same as before, correct? But there's an extra little thing in the bottom now. What's the extra little thing in the bottom?
The R factorial.
An extra r factorial. So it's the same formula as the permutations, but with an extra r factorial. Now, to really explain combinations is going to take too much time. So rather than getting into it here and having to stop in 4 minutes, let's just hold off here. So I'm going to stop recording.